All right, let's do a couple more examples with a continuous probability distribution, probability density function. We have f of x equals sine x over 2 defined over 0 to pi. Without using a GDC, we want to find the mean, median, and mode. Without the GDC? Seriously? Really? Is that what you're thinking? We can do this because we know how to graph this function. What we're looking at is f of x equals 1/2 sine x. And the graph of that, if you remember, it would have an amplitude of 1/2. And normally we go 1, 2, 3, 4. There's 2 pi, our period, there's pi, and that's where we want our distribution to stop. And our sine curve would start out at 0, 0, have a maximum at pi over 2, back to pi, and then it would, of course, dip underneath. But we don't care about that part. All we care about is here. And what we see is that this graph is symmetric at pi over 2. And what do we just get done talking about? Symmetric graphs, symmetric probability density functions are going to have equal mean, median, and modes, and they're all at that axis of symmetry. So our mean, median, and mode are all pi over 2. It can be that easy when you look at a graph. Next example. Our probability density function is f of x equals a over x squared minus 4x, defined from 1 to 3. A is a constant. I want to find a, and then calculate the expected value and variance for this distribution. Okay, well, what are we going to do? So we have to go back to our definition of a probability density function. The integral from 1 to 3 of this function, a over x squared minus 4x dx, has to equal 1. So we need to evaluate this integral and solve for a, and this isn't a great one to evaluate. U substitution isn't going to work. This isn't a sine or cosine function. This isn't the derivative of one of those, or the arc sine and all those ones that are a number over x squared minus a squared, because it's x squared minus 4x. So how do we deal? Well, we're going to go and use our GDC. And what we're going to do in here is we're going to define a couple of functions. Stay with me. F parenthesis x. Now I'm going to press Control and that button, and you see I get this colon and the equal sign. That's meaning that I'm defining f of x to be something. F of x is going to be a over x squared minus 4x. And I push enter and it says done. Yes, a defined function f of x. Now, what I really want to do with f of x is I want to integrate it from 1 to 3 and then solve for a. So here's what I'm going to do now. I'm going to define another function, and I'm going to call this one g of a. Because this is a different function name, and the variable that's going to be in it is going to be a. I'm going to do the integral, definite integral, from 1 to 3 of f of x. And I can get to f of x either by typing f of x or going into my variable menu and selecting f, parenthesis x, and I want to do this integration with respect to x, and I press enter, it says done. Remember, don't put an equal sign here. If you put an equal sign here, it will try and do stuff mathy related instead of defining these functions. Now I'm ready to solve. I'm going to go into menu, under algebra, numerical solve. And I'm going to type in, well, what am I trying to solve? I'm trying to solve g of x, or g of a, equals 1 with respect to A. And if I had a rough idea of what A was, I could put another comma and put a guess after this. I really don't without looking at a graph, so I'm just going to press enter. And there's my value for A. A is negative 1.82. And now here's an important next thing to do. I'm going to store this value as A. Now, that A has replaced the A right here, so now f of x is defined as being that big long number over x squared minus 4x. Kind of nice to have as we go into evaluate the expected value, the mean, and the variance, because now we can just type the formulas in. So I'm going to integrate from 1 to 3. And I'm going to do x times f of x dx. And we get that the mean is 2, and I'm going to store this value as some letter. I'll call it m, which is saved over the top of whatever I had saved as m before. And now to calculate my variance, that formula says we take the definite integral from 1 to 3 of x minus the mean squared. Times f of x. Dx. That's our formula that we saw previously, and now all I have to do is press enter, and we find that our variance would be 0.359 to 3 significant digits. On to probabilities now. So the total probability underneath these distributions is 1. The median is located where the 50th percentile would be, in other words, where the area is 0.5. And these areas under the curves, they correspond to probabilities. It's that straightforward. So if I want the probability that our random variable is between 1 and 1.75, we are going to integrate from 1 to 1.75 this function. And we need to solve this function for k first. And this is very similar to the previous example, but I'm going to show you a slightly different way to do it in our graphing calculator. So we're going to define a function. I'm going to redefine f of x as being 1 over x squared plus x. It says done. So I've redefined f of x. F of x is no longer that one from the previous. It is now 1 over this. And remember, our real f of x is k times this. And k is a constant. So we know that the integral, I'm going to rewrite this, k times 1 over x squared plus x dx has to be 1. So k is going to be 1 divided by whatever this definite integral is. And that's what I called f of x in my calculator. So what I need to do now is evaluate this definite integral from 1 to 2 in the calculator. And I'm going to go into my template, 1 to 2 of f of x dx, and we get this number as that area from 1 to 2. And to get k, we are simply going to do 1 divided by our answer. So k is equal to approximately 3.48, and guess what I'm going to do with it? I'm going to store it as k. And now that I have this, to find that probability from 1 to 1.75, what I need to do is the integral from 1 to 1.75 of f of x dx. And I'm going to do that in my GDC. So integral from 1 to 1.75 f of x dx. And hopefully you're saying, wait a second, f of x didn't have the k in there. You're right. That was a constant. If you look at how I displayed it right here, it was k times that integral. It's going to be the same way here. I need to put a k in front and then multiply. So our probability, and this number has to be less than 1, remember, ladies and gentlemen. If it's not, you've made a dire mistake. Our probability that a random variable falls between 1 and 1.75 is 0.838 to 3 significant figures. The last example has to do with a cumulative density function. We have a PDF being f of x equals 1 plus cosine x over pi, defined from 0 to pi. We want to find an expression for the CDF of x. Well, how do we do that? Well, remember the cumulative density function tells us the probability that x is less than or equal to some value x. So CDF is probability x is less than or equal to some value. Well, that's a probability statement. That's an integral. And this really means greater than or equal to 0 also. So we can do 0 to x, f of x dx. And f, capital F of x, we could call our cumulative density function. So I want to point something out here. The limit of integration is the same as the variable in the function. We can't have that. That's not okay. So small modification, we need to put in, we just need to use a different variable. I'm going to call this, instead of f of x, we're going to call it f of t, some other variable other than x. So we pull off our 1 over pi, integrate from 0 to x, 1 plus cosine t dt. Our antiderivative will be t plus sine t evaluated at 0 and x. And we get 1 over pi times x plus sine x minus 0 plus sine 0. And 0 plus sine 0 is just 0, so our cumulative density function is equal to x plus sine x divided by pi. Now determine an exact value. Exact means don't you dare use your GDC. We need the exact value for the probability that x is between pi over 6 and pi over 2. Well, we can use this. This is just going to be f evaluated at pi over 2 minus f evaluated at pi over 6. It's the upper limit of the integral minus the lower limit of the integral. So we have pi over 2 plus sine pi over 2 divided by pi minus pi over 6 plus sine pi over 6 all divided by pi. So we get 1/2 plus 1 over pi minus 1/4 minus 1 over 2 pi. And combining like terms by getting common denominators, we get exactly 1/4 minus 1 over 2 pi. And there is the probability that x is between pi over 6 and pi over 2. You got to remember this f of x is just the antiderivative. It's the general antiderivative for our little f of x. And that is what we're using to solve this problem.